Good evening, everyone. Welcome to IB to IIT Transition. This is my sixth video, sorry, and this is my sixth video. Previously, I think for the past 2 weeks, we have been doing this. Previously, we had done 5 more videos. The first video was on Earth, and you have a satellite which was rotating around the Earth, and we found out like what is the difference in time periods when the potential of the gravitation was seen to be increasing, and if the potential is seen to be an repulsive potential, then what is its effect on the time period? That's what we have seen in the first one. The second one which we saw was something like you have an current carrying conductor, and then this is connected to a wire, and there's an external magnetic field which the loop is being subjected to, and when you pass an electric current, the current passes through the coil, and as a result of this, you observe that there's a torque being induced. So now the interest here was to find out what was the angle made by the aerial vector of the coil with respect to the vertical. That's what we are seeing. The third problem was about the buoyancy forces. What is that we did? We looked at something like you have a container, and you had a tennis ball, you just immerse it completely. You lift your finger and the tennis ball started to move upwards. Okay, it sprang upwards, and then it went to a certain height. The interest was to find out what is the effect of this depth on the velocity of the ball. And then the interest was also to look at if there was a viscous force, then how does this velocity change? And that's what we looked into. The next question was on charge in the magnetic field. So what we did was we took up a charge, and there was a magnetic field, and when the charge enters into a magnetic field, it undergoes a circular path. Okay, it came out of the circle, and as a result of it, the question was, okay, on how does the radius of the circle depend upon the amount of charge that is being present? A straightforward question, but slightly been twisted and given to you. So that also we try to solve it across. This was your fourth problem. Okay, the next one is, the previous problem was on projectile motion. So usually projectile motion will involve something like throwing a particle, finding out what height reaches, okay, or where does it land, what is the time of flight, and so on. So this question was really a treat, okay, to say that, okay, how good was this problem? It was about two projectiles which were landed, which happened something like two projectiles were thrown, okay, in opposite direction, making equal angles and sometimes different angles, and how does the time changes, or maybe what is the x coordinate, y coordinate? We need to look into all these things. Really, if you solve one such problem, you will be able to get to know more about the projectile motion, how to utilize the projectile equations, and so on. So this was a wonderful problem to work with. Okay, and today we will start with one more problem. Okay, so this problem is about the electric potential. Those who are in IB2 students will be able to appreciate this. Those who have taken HL, okay, so you would be able to know this. There's a little bit of extra portions into it which you need to know, which you call as Gauss theorem. Without Gauss theorem, you will not be able to do this problem. Okay, but anyway, on the fly, I'll just be teaching you about what is this, and then you can proceed with it. Okay, so without wasting your time, let me just share my screen, and let me show you how do you solve such kinds of problems. Give me a moment. Okay, a thin spherical shell of radius 1 meter carries a total charge of plus 10 nanocoulomb spread uniformly over its surface. So what you have here, so you have this is a spherical shell over here, and there's a charge which is being seen over here. Calculate the electric potential at a point P located 0.5 meters from the center. Now what is the radius of this 1 meter? Where does this 0.5 meter looks? See, if this is the center over here, 0.5 meter would be at the center, in between these two. It will be within the spherical shell only. What will be the potential? Potential would be the same, okay, and from here to here will be a constant, okay, at any point inside the surface. As a result of this, this will always be equal to the potential as you observe here, as you observe at the surface. So what I can do is I can now write V is equal to KQ divided by R, which will now be equal to, what is K? K is 9 into 10 to the power of 9 multiplied by Q. What is Q? 10 nanocoulomb. 10 into 10 to the power of minus 9 divided by, what is the radius? The radius is 1 meter. 1 meter, which should now be equal to, see, this 10 power minus 9, 10 power plus 9 goes away. So you get this as 90 volts. Very simple problem. You get the answer as 90 volt over here. Okay, done. Next, calculate the potential at a point R located at 2 meters from the center. You need to find out what is the potential at a distance of 2 meters. See, this is 1 meter here, 2 meter could be this distance, right? So therefore, this is the point where you need to find out the potential, which should be given by, I have a slide here, right? Okay, I'll do it here. So here we did this as V is equal to KQ divided by R, okay, which we got this as 9 into 10 power 9 multiplied by 10 into 10 to the power of minus 9 divided by 1, which will now be equal to 90 volts. Calculate the potential at a point R located 2 meters from the center. So what did we do here? We can write V2 is equal to, once again, KQ by small r. What is the small r? If this is the sphere and this is the distance 2 meters over here. So we need to find out what is the potential at this point P. So this distance is r. So which I can once again write this as 9 into 10 power 9 multiplied by Q. What is the value of Q? The same 10 nanocoulomb, 10 into 10 power minus 9 divided by, what's the value of R? R is 2 meters. So once again, this goes away. So this should be 90 by 2 should be equal to 45 volt. 45 volt. What is the potential difference VP and VR? This was VP and this was R over here, VP and VR. So potential difference, you know, potential is a scalar. So what you can do is you can just take the subtraction of these two and thus you can write this should now be equal to 90 minus 45, which should be equal to 45 volt. Okay, very easy, right? So you just need to find out the potentials, two different cases, and finally get the value of potential difference. Okay, let me go on to the next problem. Level 1 problem was quite easier. SL, HL, anybody can do it, right? Even CBSE students can easily do this one. Then second level problem is level 2 problem. Okay, this could be an easier problem for the CBSE student because they already learned this concept. But for IB students, you have not learned this. So for this, you need to know a theorem known as a Gauss theorem. So what does it tell you? First, let us understand the problem. Then we'll go for what is your requirement. An infinitely long straight wire passes through the center of a same charge shell, linear density of lambda equal to 5 nanocoulomb per meter, points P and R are the same 2 points as in level 1. So 0.5. So this is your 0.5 meter. This is your 0.5 meter. Though I have taken some other diagram over here. So this is an infinitely long wire. Okay, and then this is 0.5 meter and this is your 2 meter. 2 meter. Treat the potential at an infinite distance from the wire as 0. At an infinite here, it is at infinity, the potential is equal to 0 here. Calculate the potential difference between 2 points in the wire. Now first, what did we do? We took up a sphere. We found out, okay, so it was like this. You took up a sphere and then this was your point R. So this was your point P. This was your point P. This was your point R. And then we found out VP minus VR. We call this as delta V1, which is equal to 45 volt. Next, what we are going to do is that we are going to replace this one with a straight wire like this, which has a lot of charge. Okay. And then now what we do is we are going to find out delta V2 for this one here. The same points are there. Okay. Instead of this one, so this is a wire which passes through the center of this. And for time being, let me assume that there is no sphere over here. Okay. And then I'm just going to replace this one here. And as a result of it, you are going to find delta V2. When you find delta V2, then what is it you get? And then, okay, so this is the second question that we are putting into class. Okay, let us do it. We're going to replace that sphere with a straight line. That's it. Let me go back to this. Now, as I told you, you need something extra to understand this. Okay, what is this? It is nothing but Gauss law or Gauss theorem. CBSE students would have already learned this. IB students might have not learned this, but this, if you learn it, then it becomes easy for you to solve these problems. Okay, so the net charge enclosed divided by the permittivity of the free space is what is given by the integral E dot dA is equal to Q divided by epsilon naught. Okay, this is what I am proposing this as your Gauss theorem. What does this actually tell you? There's something called as a flux. Okay, so you can refer to any of the physics textbooks. You'll get to know what you mean by flux. And this flux is generally given by E dot dA. Okay, in electromagnetics, you study about magnetic flux, right? So what do you study in magnetic flux? You write this as phi is equal to B dot E. That's what you write in electromagnetics. In a similar way, you have electrostatics. You have electric flux. See, B is replaced by electric field. Magnetic field replaced by electric field. And the area, I am replacing this by dA. Okay, so what did I do is that, since the electric flux is continuous quantity and you are taking a much larger conductor, So what I'm going to do is I'm going to sum up all the flux. When I do this one integration, which means I'm going to sum up all the flux. I'm taking the total flux over here. The total, I'll write this maybe if you want. Phi total is equal to the charge enclosed in a surface divided by epsilon naught. Okay, this is what you called as the Gauss theorem. Okay, hope you understand this. So this tells you this. So why do we need this theorem? We need this theorem because it helps us to compute the electric field much more easier. Now the question we should have is that if it is able to compute electric field, but we need potential over here, why do we need electric field? The reason comes in the next slide, which tells you that potential can be calculated using electric field. Okay, so therefore, first thing is we need to find an electric field. Now what do? We have a wire like this. Let me explain Gauss theorem now. We have a wire like this. I want to find the electric field acting at any point. Which are the points I want to find? Let us say I want to find at this point over here. So what I do is I will now enclose this with a Gaussian surface. I'll enclose this with a Gaussian surface. Now what is a Gaussian surface? Why do you want to do this? If you have this question, I'll tell you definitely. The Gaussian surface is one wherein, I'll write down here, Gaussian surface is one wherein the electric field is constant. Electric field is constant at every point on the surface. Okay, so therefore now if you take for example this one here, if I have a line like this, the electric field at this point is constant, at this point is constant, at this point is constant, everywhere this is constant. In other words, this defines something called as an equipotential surface. Okay, so this is what you have learned, right? You have a point charge, for example, you have a circle which you draw it across. This is nothing but an equipotential surface. And if you want a real equipotential surface, what you do? You take a sphere over there. Okay, so basically Gaussian surfaces are those surfaces which are nothing but equipotential surfaces. You need to consider the equipotential surface. By this time, I think you would have got to know how do you get that equipotential surface. You get that equipotential surface by finding out where is the potential the same, right? So therefore, for example, if I take a positive charge, where is the equipotential surface? It's nothing but a sphere that I take it across, right? In a similar way, if I take a line charge, what is a line charge? A line charge is nothing but you have several positive charges like this. Several positive charges. What I will do is, how do I know it's a cylinder? If you ask me this question, now you see, if I take only one charge over here, so what should I do? For one charge, I will draw one circle here. For the second charge here, I will draw one more circle here. Third charge, I will draw one more circle here. Now, if I keep on drawing circles one by one like this, what do you see here? You get something like a cylinder. I join all these points and I see that it forms a cylinder. At every point, it is observed that the electric field and the potential is a constant. Okay, that's what we have got. Now, so therefore, we say if you have something like this, this should be equal to Q by epsilon r. See, this is true only at a Gaussian surface. Okay, so therefore, in order to solve the electrostatic concepts or electrostatic problems, the first thing what we do is we take the charge distribution and we draw a Gaussian surface, and in that Gaussian surface, this rule is seen to be valid. Okay, and what is so advantageous of this rule? Why do you want to do it? We don't want to do it because when in a Gaussian surface, E is constant. When E is constant, I can remove this E from the integration, right? I can remove this E from the integration. You know, doing integration, doing math is really tougher. So what you can do is you can remove this one. So what do I get here? I can write E into integral of dA is equal to Q times epsilon naught. I'll get something like this, right? So therefore, what is Q? Q is a total charge percent. It's not one charge, total charge percent on this one here. Okay, now what we'll do is, let me see, I have, okay. So let me assume, okay, if lambda is the charge per unit length. What do you mean by this? Lambda is not wavelength. Okay, lambda is a quantity that we use over here. Lambda is a charge per unit length, which means I take up the total charge. Let us say there is 10 nanocoulomb over here, and total length, let us say this is 10 centimeter over here. Okay, I have told you that this will be, let us say for example, this is 10 nanocoulomb is a total charge divided by, let us say this length of the wire is 10 centimeter. Then what is the value of lambda? Lambda is 10 and 10 goes away. I get this as a 1 nanocoulomb per centimeter. Maybe I can convert it into meter, and I can say this should now be equal to 100 nanocoulomb per meter, because 1 centimeter is 1/100th of a meter, so it goes upwards, and thus you get this as 100 nanocoulomb per meter. Okay, so we have done all this now. Okay, we know what's the value of lambda. This, how do you get lambda? Lambda is nothing but, now lambda is charge by length. In other words, in general, I can now write charge is equal to Q divided by R, right? Q divided by R, or maybe if the length is L over here, I'll write this as L over here. Q divided by L, the charge Q is equal to lambda into L. I can write like this over here. So what I will do is, so I'll replace this Q by lambda into L over here. Lambda into L, I'll retain this epsilon naught as such. Now this dA, what is dA? dA, as you see, it's a small patch, it's a small area that we have. Now if I want to find the area of the cylinder, what's the area of the cylinder? 2 pi r circle divided by the, multiplied by the length of the cylinder, right? So you stack different circles one by one, each and every circle you put it across, you get a cylinder. So therefore, it should be 2 pi r into L. Thus you have E into 2 pi r multiplied by L will give you this one. So this L and this L goes away, and therefore I get this as E is equal to lambda divided by 2 pi epsilon naught r. What have we got? We have got the electric field at a point over here. Okay. In terms of lambda, what is lambda? Lambda is the charge per unit length. 2 pi epsilon naught is constant. And this r, what is r here? The radius of the cylinder that I have considered, right? Radius of cylinder or radius of the charge that we have. Okay, so we have got all this. Now let me proceed further. Now what is it we have got? We have got the electric field. We have got the electric field, which is given by lambda divided by 2 pi epsilon naught r, where r is the radius of the cylinder. We have got this. Now from this expression E equal to minus dV by dx, I can also get the potential V is equal to minus infinity to B of E dot dl. Okay, so this is nothing but you have this something like this over here. When you say velocity is equal to dx divided by dt. Okay, this is how you define your velocity. Now what you can do? You can write V times dt is equal to dx, and you can write x equal to integral V dt, right? So here you see this is E times dx. I can now do the same thing over here. I'll multiply this by E times dx is equal to dv, or I can now write integral of E dot dx is equal to V over here, right? Now these limits, how do you get this? Okay, this tells you, so whenever you want to find something over here, you need to write down the limits, right? So without the limits, it has no use. But anyway, just keep it aside. We will see, okay, how to get rid of these limits and what to do with this. Okay, we'll do this. Don't worry about the application of the limits. How do you get it and so on? Because we are doing some problems in physics. Okay, when it comes to physics, you should be able to interpret more. Okay, when you want to interpret, something would be given there, and making use of it you can use. Okay, so no need to worry about how do you get this limit, how do I solve this. No need to worry about all this. Okay, so now we have done until here. Now let us read the problem. So the same problem what I have put it there. So same thing I'm putting over here. This line is not there. So through the center of the same charge cell, this line is not there. This I want to introduce when it comes to the next one. The final problem when I come there, I'll just introduce this one. Until now, I'm not going to put this. Wire passes through, okay, the center, but there is no charge shell over here. Which means what? You have, okay, let me change my pen so that it's clear. Okay, so now you have a charge wire like this, and then it's passing through somewhere. And then what you do is, this is your center O. From here, this is the point P. So this is the point R, which is 0.5 meter. And there is one more point P here, which is at a distance of 2 meter here. 2 meter over here. And what is he asking? Treat the potential at an infinite distance from the wire as 0. He is giving you something here, which tells you V infinity equal to 0. Calculate the potential difference between the 2 points in the wire. Okay. He is once again asking you Vp minus Vr is equal to what? Is equal to what? So there also we did the same thing, right? Here also we are going to do the same thing over here. Now towards it, now Vp minus Vr equal to what? Now we know what is that? We know what is that we have learned so far. We have learned the electric field at any point. If I take an electric field at this point, we have known that it is equal to lambda divided by 2 pi epsilon naught r is nothing but your electric field. This is what we know. Now we also know that the potential can be calculated, because we want potential here. It can be calculated using integral of E dot d, what is that with E dot dr, E dot dr. Okay, so and there is a negative sign here. There's a negative sign here. See, are we doing it correctly? Minus of E dot dl we have. I have taken E dot dr because dl refers to the distance over here. Okay, now we have this much over here. Let me substitute this value. I'm not putting the limits over here for time being. So I'll write this as integral of minus of lambda divided by 2 pi epsilon naught r into dr, which should now, see, lambda is a constant. It is not changing. I'll remove this minus lambda divided by 2 pi epsilon naught into integral of 1 by r into dr. So what do I get here? This should be minus lambda divided by 2 pi epsilon naught into log r. That's what I get. Now what I can do is, what is this log r? And there should be a c here, a constant of integration. Now what does it tell you? It tells you whenever whenever we consider, okay, what is this point over here? So what we do is, when the potential, when I consider the point at infinity, the potential is seen to be 0. That's what it says. So therefore, so let me write it down over here. Let me write it down over here to make this clearer, because I have not applied the limits over here. I said that V is equal to 0. In the question it is given, right? 3, the potential at infinite distance from the wire is 0. V equal to 0. R is equal to infinity. That's what it says. Making use of this, I can find out the value of C. Okay, so what I will do is, I'll put 0 in this equation. 0 is equal to minus lambda divided by 2 pi epsilon naught into log of infinity plus 0. Now what is log of infinity? Log of infinity is 0. Okay, ln of infinity, log of infinity is 0. If you want, you can try it out. Okay, so and get back to me. So this should be 0. Thus the value of C would be equal to 0. Now what is that we have got? We have got this value of V should be equal to, because you know, upper limit minus lower limit, you can take V is equal to lambda by 2 epsilon naught into log r. Okay, so the negative sign gets cancels because it is V infinity minus VA. So that gets cancels off, and thus you get something like this over here. Now what is the next thing? We just need to substitute everything, right? The value of lambda is given to you. Okay, so I will write this as equal to, what is the value of lambda? Which is 5 nanocoulomb per meter. It's already given to you. 5 into 10 to the power of minus 9. 5 into 10 to the power minus 9. And this is 2 pi epsilon naught. What I will do is, we know that 1 by 4 pi epsilon naught is equal to 9 into 10 power 9. Okay, this electrostatic constant, we already know this. Okay, so what I do is, you have 1 by 2 pi epsilon naught over here. If I multiply this by 2 here, this will have become 4 here. This will have become 4 over here. So therefore 1 by 4 pi epsilon naught would be 9 into 10 to the power of 9 once again. And there is already a 2 here. Okay, so I put equal to here so that this doesn't mess up. 2 into, and then you have log r. Okay, so ln r, I'm sorry, it's not log. If you take integration, it will be ln over here. So ln of, what's the value of r? So if I want to find the potential at this point, okay, this would be ln of 0.5. Okay, now if I want to find the potential at this point, then this would be the same one. Let me call this as V1 over here, and I'll get V2 over here, which would now be equal to the same 2 into 5. I'll write down if you want. 2 into 5 into 9. This 2 goes away. Okay, into ln of 2 over here, right? 2 over here. And then what is it I need to do? Similar to what we had done earlier, we just need to subtract one from the other. V2 minus V1, if we do, we'll get the final answer. I'll do one thing, I don't have space, I'll write it over here. So what do we have here? We have 2 into 5, 10, 10 into 9 is 90. This should be 90 is equal to 90 minus, and what do I have here? 2 into 5, 10, 10 into 9, 90, and this is also 90, but here you have ln 2 and here it will ln 0.5. So 90 into ln 2 minus ln of 0.5. Okay, so when I do this, I get this as ln into ln 2. I'll just write ln 2 itself, minus what is ln of 0.5? Ln of half, right? I don't think I'll take the next slide and do it because it's so clumsy over here. We'll do this one once again over here. Okay, so I have come to the final problem. Okay, okay, I'll write it over here. We change my pen over here. Right. Okay. So we had V1. What was the value of V1 here? V1 was 90 ln 0.5. V1 was 90 ln 0.5, and V2 was 90 ln 2 over here. What is that I need? I need V2 minus V1, which should be 90 into ln 2 minus ln 0.5. Okay, so which should now be equal to 90 into ln 2 minus ln of 0.5 would be ln of half, which should once again be 90 into, this is ln A minus ln B. What is this now? This is natural Neperian logarithm. That's why I call it as ln. Okay, it's not log. Okay, it is log x to the base e. That's what it tells you. So this is log A minus log B should be log A by B, which should now be ln of 2 divided by half, which should now be equal to 90 ln 4, which should be 90 multiplied by 2 ln 2. Now 2 into 90 is 180 ln 2. The value of ln 2, if you use your calculator and get this value, this comes out to be around 180 into 0.7. When you calculate this, how much will you get? 180, 18 sevens are. So let me take up my calculator. Okay, just a minute. I have my mobile with me. Let me just find out what is the value of the 0.7. So 180 multiplied by 0.7 will be 126. So I get this as 126 unit is nothing but volt. That's the final answer for this one is 126 volt. Now what we have done, let me tell you once again, we have taken one wire, it is completely charged. Okay, and then we found out at this point, let me say this is R and this is P. We found out what is the delta V1 due to the wire. Let me write delta V1 wire is equal to 126 volt. This is the last one that we did. Then we had taken one sphere. Okay, and at the sphere, the same distance over here, same distance, point R and point P, and delta V sphere, hollow sphere, how much did we get? We got this as 45 volt, right? Let me go back to here, 45 volt. Okay, so we got this as 45 volt over here. So 45 volt over here. Okay, now let us read the actual problem of an IIT. So previously also it was a slide was shown, but anyway, let us read through this one here. So what does it tell you? An infinitely long thin wire having a uniform charge density of length of 5 nanocoulomb per meter is passing through a spherical shell. So what has happened over here? So you have a spherical shell. In between, there is a wire which is passing through. So what did I do? I just took up these two problems separately and discussed this. Now it is passing through it. Okay, that's what it says. A 10 nanocoulomb charge is distributed uniformly over the spherical shell. If the configuration of the charges remains static, the magnitude of the potential difference between P and R in volts. The major area of confusion people always look at is, they always think, okay, if this has a 10 nanocoulomb and this has a 5 nanocoulomb, does this charge influence this charge? Okay, of course, don't consider this because you are talking about the potentials. So potentials are scalar values and it will not influence anything over here. So therefore, due to the charge on the sphere, we have got delta V1. Okay, at these 2 points. See, I'm not looking at these points. I'm looking at these 2 points, the potential difference over here. Okay, delta V1 was seen to be how much? 45 volt. And due to this wire, it is found to be delta V2 is equal to 126 volt. So what should I do? Scalars can always be added. When I say what is the total field, I can just add this one. So when I add these two, so this becomes 6 plus 5 is 11, 171 volt. Okay, so the answer is 171 volt. That's it. Okay, appear to be very simple. So what was the difficulty you had in this? The biggest difficulty is that you are learning something very new. What was it? The new thing you learned about what do you mean by a cylinder? So what do you mean by a Gauss theorem? How do you apply the Gauss theorem over here? And then how do you get the answers over here? And integration, you already learned it. Okay, nothing new for you, but only thing is you did not apply it in the physics problems. So this is where the problems of, when you say I want to do something in IIT level, and this is where it comes over here. So from the year 1 onwards, okay, when you start solving the problems relevant, okay, with respect to the calculus, so if you incorporate calculus in your problems, then I think this should not be very difficult. Okay, so with this, I think we have come to an end to solving this particular problem. If you really like this video, do like, share, and subscribe to my channel. So we'll be releasing more number of videos, and do comment on this. Okay, like how was it pace about it? So was it really interesting? So maybe until September I'll be doing only these kinds of problems, and after September once again we'll come back to the IB, because most of the schools do open at the time. So we'll be starting with that. So until then we'll be doing the same thing. Okay, thank you everyone for being with me. See you in the next problem. Thank you.